In 2017, an object called ʻOumuamua slipped through our solar system, and it looked like nothing we'd ever seen. 2 years later, another visitor arrived from interstellar space, 2I-Borisov. But this time, it looked completely normal. A comet, like the ones we've studied for centuries. 2 visitors, 2 completely different stories. One bizarre, one ordinary. And that changed everything. Because if one looks just like our comets and one looks like nothing we can explain, what does that tell us about the trillions of objects drifting between the stars? The discovery happened on August 30th, 2019, at a small private observatory in Crimea. Gennady Borisov, an amateur astronomer and telescope maker, was conducting his routine sky survey when he spotted a faint, fuzzy object moving against the background stars. It looked like a comet, but its motion was unusual. Within 48 hours, observatories around the world confirmed what Borisov suspected. The object was moving too fast to be bound to the sun. Its trajectory was hyperbolic, just like ʻOumuamua. On September 11, 2019, the International Astronomical Union made it official. The object was designated 2I-Borisov, the 2I meaning second interstellar object. It was only the second confirmed visitor from another star system in human history. But unlike ʻOumuamua, this one came with a gift: time. ʻOumuamua had been discovered on its way out of the solar system. By the time scientists realized what they were looking at, it was already too late for detailed observations. But Borisov was spotted on its way in, still months away from its closest approach to the sun. This meant astronomers would have a rare opportunity, months to study an interstellar visitor in detail. Every major telescope on Earth and in space immediately retargeted. The Hubble Space Telescope captured the first detailed images in October 2019. The images showed exactly what you'd expect from a comet: a bright nucleus surrounded by a glowing coma of gas and dust, with a tail streaming behind. The ʻOumuamua Observatory in Chile measured the comet's composition using radio waves, detecting carbon monoxide, water, and other familiar molecules. The Very Large Telescope in Chile analyzed the light reflecting off the dust particles. By November 2019, scientists had gathered more data on 2I-Borisov in 2 months than they'd collected on ʻOumuamua during its entire passage through the solar system. And what they found was both reassuring and puzzling. This interstellar visitor looked remarkably normal. But here's where it gets interesting. Scientists didn't just find a normal comet from another star system. They found something that looked too normal. In December 2019, a team led by astronomer Martin Bannister analyzed the detailed spectroscopic data from 2I-Borisov. They published their findings in Nature Astronomy. The comet's composition wasn't just similar to solar system comets, it was nearly identical. The ratio of carbon monoxide to water matched comets from our own Oort cloud. The dust particles had the same properties as dust from solar system comets. Even the rate of outgassing fell within the normal range we'd expect. It was like finding a car from another country that uses the same fuel, same materials, same engineering, built thousands of miles away, yet functionally identical. Astronomer Dennis Bodowitz from Auburn University told reporters in January 2020, "If you put Borisov next to a solar system comet and didn't tell me which was which, I couldn't tell the difference." This revelation changed everything scientists thought about planetary system formation. For decades, astronomers assumed that conditions around other stars would be different enough to produce comets with noticeably different compositions. Different temperatures, different amounts of water, different chemical abundances in the protoplanetary disk. But Borisov proved that assumption wrong. Comets from another star system, formed around a completely different sun in a completely different molecular cloud, billions of miles away, look exactly like ours. This meant the processes that build comets are universal. The same physics, the same chemistry, the same outcomes, across the galaxy. In March 2020, researchers at the National Astronomical Observatories of China published a comparative study analyzing both interstellar visitors. Their conclusion was striking. If Borisov represents typical interstellar comets, then ʻOumuamua is the anomaly. Borisov showed us what normal looks like, and that made ʻOumuamua's strangeness even harder to explain. Because now we know interstellar objects should behave like Borisov. They should have tails, outgassing, normal compositions. So why didn't ʻOumuamua? The question shifted from, is ʻOumuamua artificial, to why is ʻOumuamua so different from what we now know is normal? And that's a much harder question to answer. The scientific community's response to 2I-Borisov was dramatically different from their response to ʻOumuamua. This time, there was consensus. In April 2020, an international team of 61 astronomers from 43 institutions across 18 countries published a comprehensive study in Nature. Their conclusion: 2I-Borisov is chemically indistinguishable from comets that formed in our own solar system. NASA's Jet Propulsion Laboratory released a statement in May 2020 calling Borisov the Rosetta Stone for interstellar objects. Mission scientist Davide Farnokia told reporters, "Borisov gives us our first ground truth. Now we know what interstellar comets should look like." The European Space Agency convened a special workshop in June 2020 to reassess the Comet Interceptor mission in light of Borisov's findings. ESA scientist Michael Cooper stated, "We now have confidence that intercepting an interstellar comet will yield scientifically valuable data comparable to local comets." China's response was equally significant. In July 2020, the China National Space Administration announced increased funding for the Interstellar Object Detection and Analysis Program. Chinese state media quoted CNSA spokesperson Wang Wenbin. 2I-Borisov proves interstellar visitors are accessible for study. China must maintain capability to detect and analyze these objects. The Chinese Academy of Sciences published a strategic roadmap in August 2020, outlining plans for dedicated interstellar object surveys using the Fast Radio Telescope and proposed space-based infrared missions. Lead researcher Quanji Ye, who had worked on both ʻOumuamua and Borisov observations, told Xinhua, "The difference between these two visitors tells us the next 10 detections will be crucial." Russia's Roscosmos issued a statement in September 2020, emphasizing that Borisov's discovery by an amateur astronomer demonstrated the need for distributed observation networks. Deputy Director General Sergei Krikalev told TASS, "We cannot rely only on major facilities. Amateur astronomers are essential partners in this search." Japan's JAXA announced in October 2020 that future sample return missions could potentially target interstellar objects if detection capabilities improve sufficiently. Mission scientist Makoto Yoshikawa noted, "Borisov showed these objects are not fundamentally different from targets we've already visited." But the most significant response came from the broader astronomical community. By November 2020, over 120 scientific papers had been published analyzing 2I-Borisov, more than 10 times the number published on ʻOumuamua in the same time frame after discovery. The reason was simple. Scientists trusted the data. Borisov behaved predictably, matched existing models, and confirmed theories. It was everything ʻOumuamua wasn't. Yet paradoxically, this made ʻOumuamua more puzzling, not less. Because now scientists had proof that interstellar visitors should be normal, which meant ʻOumuamua's strangeness couldn't be dismissed as just what interstellar objects are like. The debate over ʻOumuamua reignited with new intensity. Abraham Loeb published an editorial in Scientific American in December 2020 titled, "Borisov Makes ʻOumuamua's Anomalies Harder to Ignore." His argument: if the second interstellar object is normal, the first one's weirdness demands explanation. Other scientists pushed back. Stephen Desch from Arizona State University told Nature in January 2021, "Sample size of 2 is not enough to call anything typical or anomalous. We need dozens of detections before drawing conclusions." And that became the consensus position. We need more data, more visitors, more observations. The age of interstellar astronomy had begun, but we were still in Chapter 1. So what did 2I-Borisov actually teach us? Beyond just being normal, its data revealed something profound about how the universe works. The comet's chemical composition told a remarkable story. In February 2020, researchers using the ALMA observatory detected high concentrations of carbon monoxide in Borisov's coma, higher than most solar system comets. This suggested it formed in an extremely cold environment, far from its parent star, similar to our Oort cloud. But here's what made that significant. Carbon monoxide is one of the most volatile molecules in comets. It only stays frozen at temperatures below -250 degrees Celsius. The fact that Borisov retained so much CO meant it had been stored in deep freeze for billions of years, preserved since its formation around another star. Giovanni Rossotti from the University of Leiden published research in March 2020 analyzing what Borisov's composition tells us about its birth environment. His team concluded the comet likely formed in a cold outer region of a planetary system very similar to ours, beyond the equivalent of Jupiter, where water ice and volatile molecules could accumulate. This was the first direct evidence that other planetary systems have the same architecture as ours: warm inner regions where rocky planets form, and cold outer regions where icy bodies accumulate. In April 2020, spectroscopic analysis detected cyanide compounds in Borisov, the same organic molecules found in solar system comets. These molecules are building blocks for more complex chemistry. Their presence in an interstellar visitor proved that the same prebiotic chemistry exists throughout the galaxy. Astrobiologist Stephanie Milam from NASA's Goddard Space Flight Center told reporters in May 2020, "Finding familiar organic molecules in Borisov means the chemical ingredients for life aren't unique to Earth's neighborhood. They're everywhere." The dust particles in Borisov's tail revealed another surprise. Analysis showed silicate grains nearly identical to dust from Comet Halley and other well-studied solar system comets. This meant the dust formation process, tiny particles condensing from gas in protoplanetary disks, produces the same results regardless of which star system you're in. Planetary scientist Jessica Agarwal from the Max Planck Institute analyzed Borisov's dust properties in June 2020. Her conclusion: the physics of dust formation is universal. Temperature, pressure, and chemistry combine the same way everywhere. But perhaps the most profound discovery came from measuring how fast Borisov was losing mass. As the comet approached the Sun, it released about 40 kilograms of water per second, and 90 kilograms of dust per second. These rates match predictions based on solar system comets perfectly. This meant scientists could now model interstellar comets using the same equations they use for local comets. The laws of physics don't change between star systems. In July 2020, researchers published a study calculating Borisov's orbit backward through time. They traced its trajectory back millions of years, trying to identify its home star system. The best candidate, a red dwarf star about 13 light-years away in the direction of the constellation Cassiopeia. By August 2020, scientists had analyzed Borisov's trajectory around the Sun in detail. The comet's path took it within 2 astronomical units of Earth, about twice the distance to the Sun. Close enough for detailed observations, but unfortunately, not close enough for a spacecraft intercept with existing technology. That near miss highlighted both the opportunity and the challenge. Interstellar visitors do pass through our neighborhood, but catching one requires perfect timing, rapid detection, and spacecraft ready to launch on short notice. The lesson was clear. Next time, we need to be ready.
So what did these 2 visitors really teach us?
ʻOumuamua showed us that the universe can still surprise us, that even after centuries of astronomical observations, nature, or perhaps something else, can produce objects we've never imagined. It reminded us that our theories are incomplete, our models have gaps, and the cosmos is stranger than we thought. Borisov taught us something equally profound, that the universe follows rules, that the same physics, the same chemistry, the same processes operate everywhere, that a comet from another star system can look exactly like our comets because the laws of nature are universal. 2 visitors, 2 opposite lessons. One said, expect the unexpected. The other said, expect the familiar. And somehow, both are true. That's what makes this moment in history so remarkable. We're the first generation of humans to know, with certainty, that objects from other star systems visit us regularly. We're the first to study them. We're the first to realize the galaxy is connected by flows of matter we're only beginning to detect. Think about what that means. Every comet, every asteroid, every grain of dust carries information about where it came from. Some formed here, in our solar system. Others traveled for millions of years from stars we'll never visit. And we can't tell them apart just by looking. They're that similar. Which means the galaxy isn't a collection of isolated islands. It's an ecosystem. Material circulates, chemistry spreads, and maybe, just maybe, life's building blocks have been traveling between stars since the universe was young. We don't know yet if panspermia is real. We don't know if life originated once and spread, or sparked independently on countless worlds. But we know now that the mechanism exists. Organic molecules can survive the journey between star systems. That changes everything about how we think about life in the universe. Oumuamua is gone now, billions of miles away, heading back into the darkness between stars. Borisov is gone too, carrying its cargo of pristine ancient ice back to the void. But they left us with something, questions we couldn't have asked before, and tools we didn't know we needed to answer them. The next visitor is already out there, somewhere, traveling toward us, and this time we'll be ready.
But here's what neither Oumuamua nor Borisov could tell us. How many more are out there right now? In 2025, the Vera Rubin Observatory will begin its mission to scan the entire sky every 3 nights. Scientists estimate it will detect 5 to 10 interstellar objects per year. That means, within a decade, we'll have discovered more interstellar visitors than all of human history combined. But there's something even stranger out there. Something that doesn't just visit our solar system.
something that never had a home at all. Rogue planets. Worlds ejected from their birth systems, wandering the galaxy in permanent darkness. Astronomers estimate there could be billions of them, more rogue planets than stars in the Milky Way. Some were kicked out by gravitational interactions with giant planets. Others formed alone in interstellar space, never belonging to any star. And a few might even harbor life, surviving in underground oceans heated by radioactive decay, completely isolated in the cosmic void. In our next video, we'll explore these wandering worlds, how they form, how we're starting to detect them, and what it would mean to find life on a planet that's been drifting through the darkness for billions of years. Because if ʻOumuamua and Borisov taught us anything, it's that interstellar space isn't empty. It's full of travelers we're only beginning to discover. Thanks for watching Orbital Atlas. If you want to stay updated on cosmic mysteries and space exploration, subscribe and turn on notifications. And let us know in the comments, if you could send a mission to intercept the next interstellar visitor, what would you want it to study first? We'll see you in the next one.